Welcome to Career in Economics. Today we reach the most interesting part of the Cournot model probably. So today we are going to discuss the game theoretic version. Obviously it's not, as I said in the first class, it's not very different from the model that we discussed in the first class, but obviously the analysis is different, and the analysis is different at only one aspect, and that aspect is the equilibrium. Okay, so I said that the way we analyze the equilibrium in the basic Cournot model is wrong. Essentially it has some mistakes, so scientifically speaking it's wrong. Although the equilibrium point, that point will become the equilibrium point, the reaction curves, they will be there, everything is same, but what we know as stability analysis in standard economics, what we know as the stability analysis, this analysis of Cournot is wrong, and because it is wrong we are interested in game theoretic version. Interestingly, the game theoretic version was obviously not there till John Nash. So after his work, it came into being and we understood what would have been the correct explanation. Okay. So what was our stability analysis? So let's go back to what Cournot said to be the stability condition. Okay. And the stability condition was, put it simply, RA, that is the reaction function of A, is steeper than RB. So you can revisit the first class and see what happens when we take this and what happens when we take the otherwise. But for the time being, I'll also just show it in a very small way. So let's say this is my diagram of reaction functions. Okay, so here it is RA, which is steeper, and then RB, which is flatter. And say I'm starting with some QA naught. So if this is my QA naught, then the reaction to this will be from RB, which is QB naught. To that, the reaction will come from RA, say which is QA1. Following that, there will be QB1, so on and so forth. So it will be like in this direction, then left, then up, then left, then, and in this way it reaches the equilibrium, let's say E star. And if we start with some RB here, let's say some QB dash, then also you can find the same thing, that it will, if this is the point, alright, if this is the point, let's take some. So if I start from here, then reaction of A, from that reaction of B, then A, so it will go like this, first right, then down, then right, then down, and it will eventually reach our favorite E star. So what we see is that there is the issue that E star is the equilibrium. Alright, I said there is no issue with that. Now let's go a little bit deeper into what is the way of reaching this equilibrium. Okay, so how do we reach this equilibrium? The reaching of equilibrium, and here is the catch, must happen. Okay, must happen in stages, right? Must happen in stages, because obviously this is what we are saying, that farm 1, okay, let me write it down. So farm A, if I write it down, farm A announces QA naught, assuming that farm B will not do anything, and then farm B announces against QA naught, QB naught, announces QB naught against QA naught, and hopes that farm A will do nothing. And then farm A sort of re-announces QA1 against QB dot, and it goes on like this until it reaches E star, say QA star, comma, QB star. Okay, let's keep it like that. Let's write it like this. So here is our QA star, and here will be QB star. I'm not writing it because it will make this axis only clumsy, the vertical axis only clumsy. Anyways, so this is the process. Now, this process involves an element of time, right? Because, I mean, one announces, then obviously the other one observes, then the other one kind of optimizes, and then says, and then. So it has a time element. So typically speaking, this is a dynamic process. This is a dynamic process. It will take time. Now, one of the standard and very potent criticism of all this, all this way of reaching this equilibrium is that obviously it will be dynamic, that much we can understand. Now, that poses a second difficult question, is that, you see, farm 1 here announces QA naught and assumes that there will be no response from B side. Then B responses. And then again, farm A responses, and then again farm B responses. Now, with this chain reaction responses, with these related responses, why it is that at every stage, even having the response of B, A is assuming there will be no response of B, and B is assuming there will be no response from A. So their assumption must not hold, if they are sensible, if they are learning, it must not hold as they are going through this dynamic process, right? So somewhere this process should should come to them very differently. But all of those things they are completely missing. They are basically idiots. Okay, they see every time that their assumption is not working, and still they are assuming it. So either they're idiots or they're simply not ready to handle something economic. And this is a dynamic process. Now, in the model, in the Cournot model, where is time? There is no time, right? But Cournot model is a static model, is an out and out static model, right? So where is the problem? I said in the first class that we are dealing with a quasi-dynamic or quasi-static model, what we will say. So the static nature of the model, it is getting lost through this equilibrium reaching process. So where we are making mistakes, or where everything is going wrong? Obviously this analysis is wrong, definitely, but there is something more, right, within this analysis which is wrong. So what is it? Now, what is wrong? So let's say the mistake. What is wrong is that we are not dealing. Okay, this is what we are not dealing with individual optimization issues only. All right. So obviously there is an issue of optimization where each firm is maximizing profit. That part is there. But this is not an individual optimization issue only. We are not dealing with independent optimization, something that you observe in monopoly or in perfect competition, right? That's something that is not happening here. So what is happening here is that this individual optimization obviously is there, but it works in a dependent way, which makes it a strategic situation. Okay, so these two forms are strategically dependent. Unless we bring in these strategic dependence into the individual optimization problem, we are solving it in a wrong way, and this is what brings in game theory. Okay, so let's see how it is done using game theory. Obviously, as I said, the stability condition will remain the same. This analysis, it will change completely. Okay, so now that we are convinced that this model involves strategic interdependence, and we are using game theory, we are using the idea of Nash equilibrium. Okay, this one here is our Nash equilibrium. We must first categorize as to what kind of game we are dealing with. Right? So this model is definitely a game. Our question is what kind of game it is. Okay, now we have two farms. So definitely there are two players, right? So our n equal to 2 sort of. Then we see that they are not going for a joint profit, right? So there is no collusion. If you are interested in the collusion equilibrium, you can watch the problem solving class. Okay. Now here we are non-collusion. That means we are dealing with a non-cooperative game, and that's why Nash equilibrium. Okay. And in a cooperative game, we will be searching for something very, very different. Anyways, so two players, non-cooperative game. Now, this game here, it is being played only once. So we will say it's a one-shot game, right? So the farms, they are getting only one chance of playing this. All right. So we are dealing with a two players, one-shot, non-cooperative game. Okay. Now, obviously, had it been a repeating game or repeated game, okay, we can, ask these questions like when, can they collude, when will they collude, and what can be the stability condition, that is the strategy, so that, in a repeated game, they will go for joint profit, so on and so forth. Okay, but our basic Cournot model that we discussed in the first class, that is two players, one shot, non-cooperative game. Alright? Okay. Now we are looking for Nash equilibrium. But before we go into that, there is a very, very important assumption before finding Nash equilibrium, which is the assumption of rationality. And this rationality has to be mutual, in the sense that A will assume that B is rational and B will assume that A is rational. Remember that if this assumption of rationality doesn't work, then even when you find Nash equilibrium, in reality, these two forms may not reach it, simply because one of them is assuming something wrong about the other one. Alright? So that means if there is a wrong assumption, we will see it in the practical scenario. Alright? Something that was missing earlier, we saw that A is assuming wrong and yet not learning. So there is no such issue. And obviously this is not an equilibrium which is reached in stages. Anyways, so Nash equilibrium. So the response, I'm going to write it in English because there's a very easy way of writing it in mathematics, but that expression really tells very little about how to deal with this situation. So the response of player 2, for us it will be B, so let's write just player B, of player B against against A okay, the response of player B against which the response of player A is the best response of A. We will say this is BR with subscript A. The best response of A has to be, so we have to we put a semicolon, has to be the best response of B. Okay, let me write it fully. The best response of B. So the response of player B against which the response of player A is the best response of A has to be the best response of B against that response of A. Obviously it is confusing, but if you go deeper it will make sense. It's actually very difficult to come up with this English sentence, but language helps. That is, best response of A against some QB star. Okay, let me write both of them. QB star is equal to A star QB star. Okay, all right. So what we are saying is that what we said earlier, that is the intersection of the best response function, and as we said that coming from optimization, the reaction functions are the best response function. So to that there is no doubt. Okay? So these are the best response functions. So the QA star, QB star at which this is solved is our equilibrium. Okay. Now, how then is this best response interpreted here? By the reaction function. So the ferns, they get one chance of doing this. They don't do it in stages. Okay, and we map through reaction functions the best responses. The Nash equilibrium of this two-player one-shot non-cooperative game is at the intersection point, and we find that. Okay, so this is the game theory version of the same Cournot model, where our reaction functions simply notes the best response of one farm against the output response of the other farms. Okay, so if we say take this best response function or the reaction function Q1 plus 2Q2 equal to 15, something that we derived in the problem solving class. So what we are saying is that this Q1, it came from the profit maximization problem of farm 2. So pi 2 maximization. So what we are looking at is the best response of farm 2. That means if I write it in this way, Q2 equal to half of 15 minus Q1, then this is best response of farm 2 against Q1. Okay, so this is how we are interpreting it. You can take the other function and you can see that that can be interpreted as the best response of farm 1. But remember, these two functions, they come from the maximization problem. So we are looking at the reaction function of 2. We know this because it is coming from the profit maximization problem of farm 2. So as I said in the start, that there is individual optimization obviously, but that is done in a strategic interdependent scenario. So we interpret Cournot model, just to summarize, we interpreted Cournot model as the two-player one-shot non-cooperative game. That's our basic model. From the maximization problem, we got the best response function. We know that this is interpreted as, like standard game theory, that this reaction function, as we know it, it's also the best response of farm 2 against several or different output decisions of farm 1. Alright, and then at the intersection we find the Nash equilibrium, which is our Cournot equilibrium. So now we can say that this, what we found for the last 3 classes, is the Cournot-Nash equilibrium. Okay, now Cournot model also has a very interesting and famous result. Okay, we have seen what happens in collisive equilibrium, we have seen what happens in monopoly, we have seen how to interpret it game theoretically, we have seen the basic model. Okay, we have seen the calculus derivation also, but after all this we have another typical Cournot problem, that is to show that if the number of farm increases, then the Cournot model will reach the perfectly competitive model. That is, the price will become the competitive price. So in the next segment, we will look at the general problem. We will also solve a numerical problem from Pindai to understand, if given a question, how to solve it. Okay? Thank you.